some extra problems for Chapter 4, and before I do these, let me just stress that these free body diagrams we'll be practicing here, they are so important. We'll be doing these pretty much for the rest of the semester, so it's important that you get drawing free body diagrams down. So I'm going to have a 20 kilogram box. It's going to be sitting on a table. What are the forces acting on this box? Well, we're always going to have the weight being mass times gravity. It has a force, a support force of the table. You can call that some normal force, F sub n, right there. And for this particular box, I know it's not accelerating, and so all of these forces, the sum of the forces, must add up to be 0. I'm going to say, well, I'm going to call up is going to be my positive, so my normal force is going to be in the positive direction. My weight, that's in the downwards direction, that's in the negative direction. So I'm going to subtract off mass and gravity right there. I can now just add mass and gravity to both sides of this equation right here and say that the normal force must be equal to mass times gravity. So the normal force is going to be equal to 20 kilograms multiplied by gravity, 9.8 meters per second squared. I'm going to end up with my normal force being equal to 196 newtons. So that's part A. Now looking at part B, I'm going to place a 10 kilogram box on top of that. So here I'm going to say, well, I'm going to call this box box 1. I'm going to call my other box box 2. You can call it 10 and 20 if you will. Let me draw all the forces that are acting on box 1. I'm going to have the weight of that box, and it's going to be supported now with a normal force, and I'll call that normal force 1. Now let's take a look at box 2. It still has its weight in the downwards direction. I guess I put a 1 and 2 there just to help distinguish. It's going to have its weight in the downwards direction. It's now going to have a normal force from the table right there, and kind of in your head that's going to be larger. It's supporting more weight. It's also going to have a force of box 1 that's pushing down on it. This force from box 1 is simply the normal force that it provides box 1 to support it. We know that box 1 is not accelerating, not moving, so we can say the sum of the forces must be equal to 0. We're going to have the normal force in the upwards direction, so force normal 1. In the downwards direction, we're going to have mass and gravity. It's in the downwards direction, so it's going to be negative. Up is positive, down is negative. So we can add mass and gravity to both sides. We can say that the normal force is going to be equal to mass of 1 multiplied by gravity. So it's going to be 10 kilograms multiplied by 9.8 meters per second squared. So we're going to get the normal force of 1 is going to be 98 newtons. Now let's take a look at box 2. It's also not accelerating. We can say the sum of forces on 2 must be equal to 0. And drawing the free body diagram, all you have to do is look at it and say, what are the forces acting on there? Well, I'm going to have the normal force 2 in the upwards direction here. I'm going to have the weight in the negative direction. It's going to be mass times gravity. And it has box 1 pushing down on it. It's got the normal force 1. Now this is going to be in the negative direction. So we can add these two guys to both sides, and we can write this equation as such. We can say normal force 2 must be equal to the weight, and we call that mass 2 multiplied by gravity, plus the normal force 1. And we've already actually written these guys out. It's going to be 196 newtons plus 98 newtons, and we're going to come up with 294 newtons. Okay, we have Newton's second law problem. We're going to have an elevator. We're going to now have it accelerating. Of course, we always draw the free body diagram. We're going to have our elevator. It's going to have its weight in the downward direction as mass multiplied by gravity, and it's going to have some tensional force in the due to the cable that's also on the motor. Now, if this elevator is not accelerating, then the force of tension will simply be equal to mass times gravity. If I want to, say, maximize the force on the motor, then what I'm going to do is I'm going to, I want to maximize that tension. I want to jerk the elevator upwards. I want to accelerate it upwards. So to do that, I'm going to say, well, the sum of the forces, in this case in the y direction, is going to be equal to the mass of the elevator multiplied by its acceleration. We're given its acceleration in terms of g right there. It's going to be tensional force in the upwards direction and mass times gravity in the negative direction. Acceleration is in the upwards direction, so this quantity right over here is going to be positive. Solving for the tensional force, the force of tension is going to be equal to mass times acceleration plus mass times gravity. Factoring out a mass, acceleration plus gravity, and now replacing my acceleration with the given acceleration, 0.068 g plus g. Simply add those g's together. I'm going to get my mass times 1.068 multiplied by g, and I can get 4850 multiplied by 1.068. All that's going to be multiplied by acceleration due to gravity, 9.8 meters per second squared. So my force is going to be equal to 5.08 times 10 to the 4th newtons. That's going to be the maximum force. Now for the minimum force, what I want to do is I want to let that elevator drop down. I don't want to have my acceleration in the upwards direction. I want to let that acceleration drop downwards. That's going to lower the tension supplied by the cable. I do the same thing. I'm going to write sum of the forces in the y direction is going to be equal to the mass multiplied by the acceleration. It's going to be the tensional force minus mass times gravity, much like I had in the last part. But now, if you look at it, my acceleration's in the negative direction. I need to put a negative sign to say, hey, my acceleration is now in the negative direction. Again, solving for the tensional force. Here I'm going to have mass times gravity, and now it's going to be a minus mass times acceleration, so a little bit different than before. So mass, gravity minus acceleration, or mass multiplied by gravity minus 0.068 g, and that's going to be equal to the mass, which is going to be 4850. Those g's are going to give me a 0.932 g, g being 9.8 meters per second squared. So that force is now going to be 4.43 times 10 to the 4th newtons. Now I have my forces in two directions, so this is going to be my tightrope walker. Draw my free body diagram. I'm going to have her mass and gravity in the downwards direction. I'm going to exaggerate the angle slightly just so it's easier to draw. I'm going to have some tensional force in the wire that is going to be supporting her. I know that this angle is going to be 10 degrees. It's also going to be 10 degrees over here. So what I can do is I can break this guy up into its x and y components. So I'm going to have a y component and an x component. Same over here. Force, tension in the y direction, force, tension in the x direction. And you can kind of see that these two guys in the x direction are going to cancel each other out. And this force of tension in the y direction is going to balance my tightrope walker out. She is not accelerating. I can write the sum of the forces on her in the y direction. That must be equal to 0, no acceleration. We're going to have force of tension in the y direction from this rope over here acting on her. And then we're going to have the force of tension in the y direction acting on her right there. and these are in the positive direction, the downwards direction. We're going to have mass multiplied by gravity. So we're going to say, well, 2 times the force of tension in the y direction must be equal to mass times gravity. I've simply added those two terms and added mass times gravity to both sides. What I'm looking for is actually not force of tension in the y direction. I'm looking for the tension in the rope. I know that the force of tension in the y direction is going to be equal to the force of tension multiplied by sine of that angle. That angle is going to be 10 degrees. So I'm going to take that and plug that in right there. 2 times force of tension multiplied by sine of 10. It's going to be equal to the mass of the tightrope walker multiplied by gravity. I'm going to divide both sides by 2, divide both sides by sine of 10. Force of tension is going to be equal to mass times gravity divided by 2 sine of 10. So I know that the mass is going to be 50 kilograms. I know gravity, 9.8 meters per second squared. Got my 2 and I got my sine of 10. And I'm going to end up with 1410 newtons. Now let's start to combine this with friction. Still, the very first thing I want to do is draw my free body diagram. So here I have a surface, it's got some friction associated with it. I'm going to apply a force. It doesn't tell me which direction, so I'll just pick one. Applying my force, that force is going to be equal to 35 newtons. Friction is going to oppose motion. I'm going to have some force of friction that's going to oppose my force. Is that all the forces acting on this box? No. We are always going to have mass, and we're always going to have mass times gravity, weight in the downwards direction, and of course that's going to be supported by the normal force of the table pushing up on it. I'm asked to find first what is the coefficient of static friction equal to. Well, first thing I can do is I can say this box is not accelerating, so I can write Newton's laws in both the x and the y direction. Some of the forces in the x direction must be equal to 0. I'm going to have my force in the positive x direction, and I have friction in the negative x direction, so I'm going to put a minus sign right there. So that tells me that my force due to friction, there we go, must be equal to the force that I applied to it, which is going to be 35 newtons. I also know that the force due to friction is going to be equal to the static friction coefficient multiplied by the normal force right there. So I can say that my force is going to be equal to static friction multiplied by the normal force. Divide both sides by the normal force right there, and I get my coefficient of static friction, which I'm looking for. To get the normal force, I say, okay, well, some of the forces in the y direction must be equal to 0. This thing's not accelerating in the y direction. I'm going to have the normal force in the positive direction, mass times gravity in the downward direction. So my normal force is simply going to be mass times gravity. So I can write my coefficient of static friction to be the force I apply to it divided by mass times gravity. So 35 newtons divided by the mass, it's a 6 kilogram box. I have gravity. Gravity is going to be 9.8 meters per second squared, and I end up getting a coefficient of static friction of 0.6. Now for part B, it says, well, this guy is going to now start accelerating, so I can't write some forces in the x is equal to 0 as I did before. Now I know there's going to be some acceleration going on, and the acceleration is going to be in the direction that I have applied my force. Still, I write Newton's second law. Sum of forces, this is going to be in the x direction. It's going to be equal to mass times acceleration. Acceleration is in the positive x direction, so I make sure I indicate this as positive. My force is in the positive direction, so I'm going to have force, and friction is going to oppose this guy. I know that I can also write this as my force minus my mu sub k now it's moving, kinetic friction, multiplied by the normal force, and this is what I'm solving for. So I'll be able to say that mu sub k multiplied by the normal force must be equal to the mass times, or I'll say the force minus the mass times acceleration. Divide both sides by the normal force here. Divide this guy by the normal force here. And I isolate the coefficient of static friction. I know that the normal force is going to be the mass times the gravity. I know my force is equal to 35 newtons. I know that the mass is going to be 6, and I know that it's accelerating at 0.6 meters per second. Here I'm going to have my 6 multiplied by 9.8, the acceleration due to gravity. And I go ahead and I type all that in, and I'm going to come up with the coefficient of kinetic friction to be less than the coefficient of static friction. It's going to be 0.53. Okay, now let's take a look at a ramp problem. So I'm going to draw my ramp right here. It's a little bit more than the advertised 8 degrees, but the exaggerated angle should help me in drawing my picture. I'm asked for how long it takes to reach the bottom, so I'm looking for a time at the end of the day. I know it's going to travel some distance. I want time, so I'm going to want the acceleration. I'm going to want the acceleration to use my old kinematics equations. In order to get the acceleration, I have to use Newton's second law. I know that this acceleration is not going to be 9.8 meters per second squared. It's not dropping straight down. So let me just go ahead and draw my my bar of soap. I'm going to draw it in the middle of the ramp. It's going to start at the top, but give myself a little bit of room. Newton's second law. First thing I do is draw the free body diagram. I'm going to have mass times gravity in the downwards direction. I'm going to have the normal force, the support force, always perpendicular to the surface. I know that the acceleration is going to be down the ramp, and it's going to have a little bit of friction. This friction is always going to oppose the motion. And with any ramp problem, it's always easiest to kind of shift our x-y axes such that the acceleration is only in the x direction. It's not in the x direction and the y direction. It just makes our life a heck of a lot easier. So what I want to do is I want to take my weight and I want to break that into its two components, the weight in the x and the weight in the y direction. So we know from trigonometry that this angle right there is going to be the same as that angle right there. So my weight in the y direction, that's going to be the adjacent side of that triangle. That's going to be the mass times the gravity multiplied by the cosine of that angle. The weight in the x direction, the weight component in the x direction I should say, is going to be the mass times the gravity times the sine of that angle. Now I can say, well, let me write Newton's second law. I'll start within the y direction. The y direction is going to be the up-down direction. There's no acceleration. The soap is not falling through the ramp, so the sum of the forces must be equal to 0. So I'm going to have the normal force in the upwards direction, and mass times gravity times cosine of theta in the downwards direction, indicated by that negative sign. So my normal force is going to be less than the mass times gravity. It's going to be mass times gravity cosine of that angle. Now let me take a look at the sum of the forces in the x direction. That's going to be the mass multiplied by the acceleration in the x direction. This is what I really want. And I'm going to have the mass times gravity times the sine of theta, my weight pulling it downwards, and friction is going to oppose that guy. I know that mass times gravity sine theta, I can rewrite my frictional force be equal to my normal force multiplied by mu sub k, and here I have my normal force in terms of the mass times gravity and the angle. So the mass multiplied by the acceleration in the x direction It's going to be the mass times gravity sine theta. That's the weight in the x direction. And then mass, gravity, cosine theta, and mu sub k. So I've simply rewritten the normal force with what I know from the y direction. As you'd expect, mass doesn't matter. And here I have now an expression for my acceleration in the x direction. So now let me think about my old kinematics equations. I know that it's going to travel 9 meters. I know that it is accelerating. Now I know its acceleration. I'm looking for how long it takes. So 9 meters, and I'm looking for the time. Take a look at my old kinematics equations, and I see the best equation to use is going to be position is equal to initial position plus the initial velocity multiplied by time plus 1/2 times the acceleration time squared. And of course I'll simplify this. I'll say it's going to start at the top of the ramp. I'm going to call that 0. It's going to have no initial velocity to release from rest. Typically, if it doesn't tell you, that's what you have to assume. And we're going to say, okay, now I know everything in this. I can solve for time. I'm going to multiply both sides by 2 and divide both sides by a. So 2 up there and an a down there. That's going to cancel out. Take the square root of both sides. So the time is going to be equal to the square root of 2 times the distance that it travels, 9 meters, divided by the acceleration. So I can plug in that acceleration that I have before, that big nasty guy. It's going to be g sine theta minus mu sub k, g cosine theta. And now I know what all these guys are. It's simply a matter of plugging them in. So the time is going to be 2 multiplied by 9 meters. I know what gravity is, 9.8. Sine, my angle is 8. Minus mu sub k, 0.06. It's pretty small. Soap is pretty slippery. And gravity, 9.8. And then it's going to be a cosine of 8 degrees. Bring my square root all the way over, and I'm going to end up with 4.8 seconds. The last problem, number 56, is going to be fairly similar to the last one. I actually even just reused a lot of the same stuff here. Got the same free body diagram. I've got an object sliding down a slope. It's got some friction. It's accelerating only 0.3 meters per second, so fairly small. I know the angle, so let's go ahead and figure out what the coefficient of friction has to be. I'm going to do the same thing I do before. Draw my picture, draw my free body diagram, and then split my weight into the weight in the x direction and the weight in the y direction. So mass times gravity multiplied by the sine of that angle. Mass times gravity multiplied by the cosine of that angle. Again, similar triangles. As before, I know the normal force has got to be equal to the mass times gravity times the cosine of the angle. I derived that on the last one. That's from Newton's second law in the y direction. In the x direction, I'm going to say sum of the forces in the x direction is going to be equal to mass acceleration in the x direction, which is going to be equal to the mass times gravity sine theta, the weight pulling it downwards, being opposed by the force of friction. So fairly simply, I just rewrite this guy solving for the force of friction. The force of friction is going to be equal to mass times gravity times sine of that angle minus mass times the acceleration in the x direction. I know what that is. So the force of friction is going to be equal to the mass, 25 kilograms, multiplied by gravity, 9.8, sine of the angle, 27, minus the mass, which is going to be 25, multiplied by the acceleration, 0.3. So my force of friction then must be 103.7 newtons. I'm also looking for what the coefficient of kinetic friction is. That's simply going to be the frictional force of friction, divided by the normal force, which I know from the sum of forces in the y direction. So that's going to be 103.7 divided by mass times gravity times cosine of the angle, or 103.7 divided by 25 multiplied by 9.8 multiplied by cosine of 27, right there. So my coefficient of kinetic friction then must be 0.48.